Okay, so the focus of my speech is on the measures of redundancy, and more specifically contrasting attributes-based versus relations-based measures of redundancy. Uh, Even if this can be seen as a very specific issue, actually, I mean, this is a piece of the conclusions of the book said by Lutz himself. My opinion, a major contribution of the study is the focus on redundancy as a measure, etc., etc. So somehow this question of the redundancy is actually central in a book that is full of very interesting things, and we all know it's because we participated in the discussion all along the book, and so it's a great book from a great scientist. So, but anyway, this is one important point with a lot of implications. So, let me start from a point which was already raised by me some months ago. That is the question that reality is made of two relatively independent dimensions. Sometimes, I mean, all of us know it, but actually it's something that deserves more attention, because there's really two different orthogonal, let's say, dimensions. One is elements-based dimension, that is focusing on single elements, and of course its attributes, the attributes of single elements. Elements can be the nodes of a network, or the parts of a system, or a single, even more elementary pieces. And the attributes are its properties, height, weight, color, or in case of companies can be income, assets, etc. And the other dimension is the relations-based dimension. And this dimension deals with the network, and more specifically with the network or the system's topology, that is the distribution of links among the nodes. And the question is that just the structure, and the structure can be rather independent on the attributes. That's why these are two different dimensions. I say I wrote here relatively independent, because actually there is an influence between the two dimensions. There is I tried to represent it here in this way. You know, I mean, in time one, a certain distribution of attributes among the elements can influence the distribution of the connections between the elements, and vice versa. So this is the arrow of time is this one. And so they are different dimensions, but can be a relation between them. So that's why relatively independent. Just to make an example that is familiar to me, let's say if there is if a company or an organization is very competitive, is very important, most likely it will be highly connected with other companies, with other institutions, other organizations. So the attributes can influence also the connectivity, and vice versa. If you are highly connected, most probably you have the best conditions to get better performance than the others, and so covering a good position in the network can improve the attributes, that is the performance of the company. So that's why it's relatively and not totally independent. Now, what's the point here is that this ontological dimension have their own measure of redundancy. And now I try to focus these different measures and then summarize what Lut did in the book, which is something new. That is a hybrid measure, a measure which is at the same time grasping the attributive aspect and the relational aspect. But what I will argue in my speech is that actually this is something interesting, but how to say, not enough. There is the core concept, the core phenomenon for system dynamics, network dynamics, for cybernetics, lies in the cycles, in the, recursivity, and not in what is the base used by Lut to build this hybrid measure. So this is basically my main point in this speech. So element-based redundancy is measured by the well-known Shannon entropy equation and its variants. The variants, I mean, for instance, the variants used by showed by Klaus in his speech in this group. And I mean, very simple words, it counts how many different elements are in and its frequency, the frequency of each element, no? And we know the very well-known equation. If we were considering many systems, we could apply this measure, and this is somehow the logic followed by Lut. That is measuring the degree of overlapping and counting how many elements they have in common. Just this picture could help to understand what I'm saying. That is in the triple helix view, no, university, industry, government. We can consider these as the subsystems of the whole system in, for example, in the evolution of a region, of a nation, or whatever. And the idea is that we are going to measure the redundancy in terms of the overlapping between these three subsystems. But Lut does something more than this. I mean, because this is somehow at the macro level. Lut tries to offer a micro approach to this hybrid measure. And that's why I call it hybrid, because going to the micro level, which is the level of the connections between the companies of the industry, the departments of the universities, a subsystem, and the government institutions, it's possible actually to combine the attributive aspect and the relational aspect. But then I will say why it's useful, but let's say not enough, or okay, then we will discuss about it. Okay, let's look at some pure relations-based redundancy, that is network redundancy, something that is not attributive, not on the other side, so not hybrid, but purely on the side of relations. So basically, we can use three types of measures. One type is measuring redundancy in terms of the share of links exceeding the minimum number to keep the network fully connected. So basically, the idea is that, and this is a measure used actually in network analysis, when you have a node, a network with n nodes, then n-1 is the minimum number of links necessary to keep all the nodes connected in the network. And this is taken as, let's say, the benchmark of efficiency, which means no So zero redundancy. So basically efficiency and redundancy are moving in the opposite direction. So if you are very efficient in the sense that you save the number of links to keep the network fully connected, so you are efficient. And if you add more links, you are losing efficiency, but you are gaining redundancy. So you have more links connecting the nodes in respect to what would be the minimum to keep all of them connected. So the logic of calling efficient or as opposed to redundant is somehow an economic logic, in the sense that keeping a relation working is time consuming, at least is resource consuming. So the less links you use, you employ, the more efficient you are, but keeping all the network connected. So a second measure of redundancy is what is called, and not so much used actually in network analysis. I mean, it's at least in social network analysis, it's very, very seldom used. But it is a measure of redundancy because it is called the cyclomatic number. That is how many cycles, linearly independent cycles, which is a particular constraint in terms of how many cycles. So basically, to say it in few words, if a cycle is included, is inscribed another cycle, then that is not more linearly independent. So you count only one. So let's say the biggest one, the one including the shortest cycle. So to say it in few words. There is a third measure, and it's very important to look at, which is redundancy in terms of the number of simple cycles. That is, in this case, we are removing the constraint of being linearly independent. And so we are counting even the cycles inscribed into in bigger, longer cycles. And this is very important because anyway, and that's one of the points I'm trying to argue and discuss with you, is that cycles are actually the fundamental ingredient to understand the complexity of a network or a system, and to understand even the potentiality of development and of new behavior of the network. So cycles are the real point of reference, which is actually the concept of recursivity. There is recursive networks. Recursive means that there are cycles inside. So, and that's why this is particularly important for cybernetics, because actually the idea of loop, feedback loop, is just a way to look at cycle, to say that there is a cycle, there is a recursion from input to outputs and vice versa. And actually, this is also the essence of self-organization. You can say that there is self-organization if there is something that is feeding back into the same system, that is into the self. That's why it's self-organization, because there is a cycle. Can be at the macro level between input and output, or can be at micro level between the elements of the system, between the elements of the network. Now, with this slide and a couple of other slides, I want to show you how these two measures are independent one another. The Shannon-like which is measuring attributive redundancy and the network redundancy. In this case, this is a typical directed acyclic graph, and particularly in the form of what Simon called the archetype of hierarchy. And as you can see, is an out tree. No, there is a root of the network, which is this one, and the others spreading from the root. And in this network, if we consider all the nodes equal one another, we have the maximum redundancy, the Shannon-like, but we have the minimum redundancy, so zero redundancy in the network, in the relation-based measure, because it's perfectly efficient. We have n nodes and n-1 links. So one is maximum and the other measure is minimum. And this is just to show you how the two measures can go in, totally diverge. This is another example. This is taken from a book I'm publishing right now. It's about the intersectoral network of ownership relationships in the EU 28 aerospace industry and with its neighbor partners. You can see here in this network, this is a very small network, just 21 nodes and only 89 links. And again, in this case, Shannon redundancy is zero if we consider each sector as a different element. So this is maximum entropy. Every node is different from the other. But in terms of network redundancy, we have, in terms of inefficiency, there is type, what I showed before, not the three measures. Type 1 measure is 17%. In terms of the second measure is 28, it's a chromatic number, it's 28 linearly independent cycles. And in terms of simple cycles is almost 16,000. So it's a huge number for such a small network like this. So again, these two measures are addressing to totally different phenomena, different aspects, so they diverge. In one case, we look at attributes. In the other case, we look at the relations. Another example, this is again the ownership relationships, the same case study as before, but instead of sectors, we have the industries involved by this network. And what we see is that, again, we can consider Shannon redundancy zero because each industry is different from the other. They are all different industries. And the network redundancy type 1 is 0.5%, so it's very low. And network type 2, that is linearly independent cycle, 76, so quite low as well, but 1.8, almost 1.8 million simple cycles. So now let's look at what the novelty of Lutz's approach, what he did. Let's go shorter. Let's look at the Lutz's reasoning. The idea is that each set of organizations sharing the same attribute can be considered as a subsystem. Let's say university, industry, government in the example. And some organization has more than one attribute. These are, let's say, the context. This is the context. In the view of triple helix model, the three subsystems interact, and its intersections, so the overlapping, represent the redundancy of the whole system. Now, what is the interesting point respect to the previous picture of the three helixes? That Lut tried to build it at the micro analytic level, just to consider the relational dimension. Lut doesn't talk in this language, in this way, but in a similar way. And the goal is the same at the very end. So even with some communication we had privately with Lut. So Lut says, so I took both things into together, both aspects, both dimensions, let's say, ontological dimensions. What is the way to do that? Lut's procedure, Lut method is to unpack the network through triads and check the distribution of attributes across the triad. So the reference unit is not more the whole subsystem or the whole system, but the triads composing and constituting the system, the subsystems. And then Lut applied the Shannon-like redundancy measure to the triads. So the redundancy between each pair of attributes, and looking at the result. That is, the information content of the system composed by three subsystems, so 1, 2, 3, then comes as component by the information content of subsystem 1, subsystem 2, subsystem 3, then the overlapping in pairs between the three subsystems, so T12, T13, T23, minus the overlapping among all the three. So this is the core of the reasoning. And so this is at the very end is a triad-based measure of redundancy. Redundancy means as attributes overlaps. So the point that is recalled by Lut even in the conclusion of the book, not only in chapter 5, but even in across in the whole book and in the conclusion, is that this is a good way to measure the synergy, and I would add synergy by overlapping, and demonstrating that synergy increases redundancy. Actually, I should say that to demonstrate it properly, he had to show that the information content of this expression is major than 0, or that the redundancy of this other, the whole system is measured than the redundancy of each separately. Maybe I couldn't find it into the book actually, and also in another paper that Lut sent me. Okay, actually, I can say that I couldn't find this final piece of the reasoning. But anyway, the idea is that one, is this one. Now, what's the point? And this is the core of my speech. This tells us important thing, of course, and but what this measure is lacking to say, it says nothing about the recursivity. That is the degree of self-organization, because nothing about cycles, dynamics, on which feedback mechanism does prevail in each of the cycles. Because in a cycle can be only positive feedback, only negative feedback, mix of the two. I mean, but this matters a lot to understand the dynamic of the network. Another question is that there can be networks full of triad-based overlapping attributes, thus with a high value of hybrid measure of redundancy, the measure proposed by Lut, but with the 0 cycle redundancy, zero network redundancy. I will show you in a while an example of this. And that's why it doesn't, I mean, this measure doesn't work if we want to grasp let's say, the essence of recursivity, the essence of complexity, I would say, the essence of cybernetics, no? The essence of self-organization. Because there can be a high value of this triad-based redundancy measure, but without any recursivity, without cycles. And that this is my main criticism on the limit of this measure. Let me jump on this aspect. Actually, I think it's possible to follow the same approach to build another hybrid attribute relational measure of redundancy by replacing triads with cycles. It could be done. Okay, it's something that could be interesting. Actually, could be useful because it moves actually the hybrid from the triad to the cycle, which is much more important in my view, much more fundamental. Actually, the point is that when Lut recalls Ulanovich triad, he does not grasp the most important aspect. That is not the triad itself, but the fact that that triad that he is using, which is this one, is a recursive triad. So it's cyclical. It's a cyclical form of that triad. And now, what's the point? What is the tricky aspect? And let's say can be misleading is that this is only one instantiation of all possible triads that we can build. There are 16 triads. So this is only one of them. This is a recursive triad. Specifically is the number 10 of the list of possible oriented triads. And one of the only 4 that include recursivity. The others are 14, 15, 16. I just show you in this picture. These are all the 16 triads that could be built. And I don't know if you see, okay. And this is the pure cycle in the example that Luke took from Ulanovich, and the others are these in the bottom. These other 3 in the bottom line, where there is a recursivity. But be careful. The point is that in all the others, 12 possible triads, there is no any recursivity. So all these others are triads, but they're not recursive triads, not cyclical. And it matters, again, it matters a lot. Okay, we can measure it, but then to get what? And I give you an example. This is again an example of directed acyclic graph. It's a pure hierarchy again. It's very clear how it is. And here we have triads. It's full of triads, but these triads are not open, are not closed. They are open. So by definition, there are no cycles. And actually, this network can generate cascades, the snowball effect, but only one way from, let's say, just so to speak, from the top to the bottom. But it lacks of recursivity. So, I mean, it's not so interesting from the point of view of self-organization. There is no self-organization here because there is no any closure, no any cycle. By the way, we could close the triads, even all of them or some of them, but still lacking recursivity. And this is just what I said before. That is, we could have triad, we could have a network with a high value of triad overlapping attributes, which is the hybrid measure proposed by Lutz, but no cycle. I could put a link here, another link here, another link here, etc. And I'm closing these for these three triads, but they are closed but not recursive. On the other way, here this is a strongly connected component, which means, I mean, the definition, it means that from any of the node is possible to reach any other node. In this, this is and in this case, we have that the type 1, the degree of inefficiency, network redundancy is low. Type 2 is moderate, but type 3, I mean, simple cycles is huge. So there are there is a lot of recursivity. Now I'm going to close the presentation. So this view, let's call it cycle-based view, is consistent, fully consistent with Kaufman's approach. There is a network density, and more specifically, a topology characterized by the presence of cycles is fundamental to decide its dynamics and the complexity of its phase space. That is, how many possible evolution can have in the over time. Kaufman too considers redundancy in this, precisely in this way, and also in two other ways, but maybe not interesting now to talk about, particularly the parameter P, which is the distribution of zeros and ones of each Boolean function insisting on each node. So because in a Kaufman approach, nodes can be active or inactive, and the canalizing function. I mean, this is just to say that there are even further measures of redundancy if we consider that nodes can be active or inactive. That's the premise, because the Boolean rules. And what's my further criticism is that the dynamics and the trajectories, which actually is at the core of Lutz's book, is a question much more complicated than a triad-based redundancy. There are too many other things so fundamental that matter so much, and respect to which, to these other aspects, the triad-based view is a sort of, I call it triadic reductionism, but anyway, a form of reductionism. Actually, this is this view is I'm well aware that it is supported, is proposed by some important scholars in social network analysis. Some of the gurus, let's say, in social network analysis, bring forth the idea that in the triads, if we decompose, which is the right word, if we any network, they say, and that's true, any network could be decomposed as a collection, a network of triads. That's true. That's true. But if you focus on single triads, you follow another form of reductionism, which I mean, instead of the single element, now the elementary unit is the triad and not the single element. But anyway, it's reductionist, because you lose The other aspect that are very, very important is exactly, I mean, this is a list of issues, not the case to go on each of them, but topology matters, the whole topology matters, not just simple the collection of triads, because you can have the same number of triads, but with different topologies. And activation rules matters, and so many, in particular, cycles matters. That's the point. The triads doesn't tell you about the cycles, and as I showed before, a triad could be a cycle itself, or even it could be not a cycle. And only 4 out of the 6 possible forms of triads are contain a cycle. The others don't. So, and that makes the difference. So my conclusion is that in order to expand the space of possibility of the evolutionary dynamics of discursive knowledge, which is exactly the goal of Lutz's book, what you have to do, I would say you have to increase its type 3 network redundancy, that is its recursivity. But I mean, getting benefiting from the work of Kaufman until the edge of chaos, because beyond the edge of chaos, you will have a chaotic dynamic, and so too unstable to be an evolving system. So the idea, the concept is evolvability. So to be evolvable, a system, a network must be at the edge of chaos. Yeah, I finished just the last slide. Maybe
Yes.
increase redundancy in terms of triad base. Okay, the subsystems overlapping could be interesting, or maybe increase also the redundancy in terms of cycle base subsystem overlapping. But this, the first point is the most important. Okay, sorry, maybe I took too much time. I'm sorry, but it was not easy for me to condense more than this. Okay, that's
All right.